Hello friends, I welcome you in lecture number 3 on series solutions of differential equations. In lecture number 2 we have discussed about ordinary and singular points of a given differential equation. In this lecture we will discuss this question on ordinary and singular points. This question was asked in GTU Summer 2019 exam. Question is, classify ordinary points, singular points, regular singular points and irregular singular points if exist of the following two differential equations. First equation is y double dash plus x into y dash equal to 0, and we know how to find out ordinary and singular points that we have already discussed in lecture number 2. So if you have not seen lecture number 2, I suggest you to watch lecture number 2 first and then go for this lecture. First step is we will compare given equation with y double dash plus p into y dash plus q into y equal to 0. If we compare this equation with this standard form, we can see that coefficient of y dash is p. So here coefficient of y dash is x, therefore function px is equal to x, and q is the coefficient of y, and there is no term containing y here, that means coefficient of y is 0. So first we have to decide, or first we have to check whether our equation is in this form or not. If it is in this form, then we will compare our equation with this equation and we will decide these coefficient functions px and qx. Now it is clear that px and qx are polynomials, so they are analytic at every point. Clearly px and qx are analytic everywhere. Clearly px and qx, they are polynomials. So we can write reason is px and qx being polynomials are analytic at every point. Analytic at every point in the real number set. That means every real number is an ordinary point of given equation. Every real number is an ordinary point of given equation by the definition of ordinary point of equation 1. And because every point is an ordinary point, equation 1 has no singular points. So we can write that every point is an ordinary point, therefore equation 1 has no singular point. Singular points are those points which are not ordinary, but here every number is an ordinary point, therefore equation 1 has no singular points. Similarly we can check for second equation, but this equation is not in standard form. First we write down this equation, xy double dash plus y dash equal to 0. Xy double dash plus y dash equal to 0. Let me check again, xy double dash plus y dash equal to 0. Here coefficient of y double dash is not 1. So first we divide this equation by this coefficient of y double dash, which is x. So we divide every term by x and we write this given equation can be rewritten as y double dash plus 1 by x times y dash equal to 0. And now we compare with this standard form, y double dash plus px into y dash plus qx into y equal to 0, and we can see coefficient of y dash is 1 by x, so px is 1 by x and qx is equal to 0 because there is no y term here. Now this qx equal to 0 is a constant polynomial, therefore it is analytic everywhere, and px is a rational function. So it is analytic at those points for which this denominator is non-zero. Denominator is simply x, so x equal to 0 will make this denominator 0, and it is non-zero at every non-zero value of x. So this denominator of this 1 by x, which is x, is 0 if x equal to 0 only. So px is not analytic at x equal to 0. Qx is analytic everywhere, but we are interested in those points at which both are analytic. So px is analytic at every non-zero point, qx is analytic at every point. That means the common points at which both are analytic are non-zero points. So we can write that px and qx are analytic at every non-zero point. Clearly, px and qx are analytic at every non-zero point. Analytic at every non-zero point. Therefore, by the definition of ordinary point, we can say that every non-zero point or every non-zero real number is an ordinary point. Every non-zero point is an ordinary point of given equation, which we can give as number 2. So every non-zero point is an ordinary point of equation 2. Now px is not analytic at x equal to 0, therefore x equal to 0 is not an ordinary point, and therefore we can say that x equal to 0 is a singular point. First we can write that x equal to 0 is not an ordinary point. X equal to 0 is not an ordinary point because px is not analytic at x equal to 0, because px, which is 1 by x, is not analytic at x equal to 0. Therefore we can write that because x equal to 0 is not an ordinary point, x equal to 0 is a singular point of given equation 2. Now once we have singular point, we can check whether it is regular singular point or irregular singular point. So for that we have to decide these two quantities, x minus 0 into p of x and square of x minus 0 into q of x. If these two quantities are analytic at x equal to 0, then x equal to 0 is regular singular point, otherwise it is irregular singular point. Now value of px is 1 by x, x minus 0 is x into px, which is 1 by x, which is equal to 1, and this is x square, and the value of qx is 0. So we have x square times 0, which is 0. So these two functions, x minus 0 times px and x minus 0 times 0 square times qx, are constant polynomials and they are analytic everywhere, and therefore they are analytic at x equal to 0. Therefore x equal to 0 is regular singular point. So x minus 0 into px and x minus 0 square into qx are analytic at x equal to 0, analytic at x equal to 0 because they are constant functions, they are analytic everywhere. Therefore x equal to 0 is a regular singular point of given differential equation. X equal to 0 is a regular singular point of equation 2. So the conclusion is every non-zero point is an ordinary point of given equation 2, and x equal to 0 is regular singular point of this equation 2. We can discuss one more question on ordinary and singular points, which was asked in GTU Winter 2019 exam. So given equation is x cube times x minus 2 y double dash plus x cube y double dash plus 6y equal to 0. This coefficient is not 1. So first we divide whole equation by this coefficient, and we will have x cube divided by x cube times x minus 2. X cube will cancel out, and we will have 1 divided by x minus 2 times y dash plus this 6 divided by x cube times x minus 2 y equal to 0. So we can give given equation as number 1, and this is in standard form. So if we consider coefficient of y dash, then we have px equal to 1 over x minus 2. Px is always coefficient of y dash, and qx is coefficient of y, which is 6 divided by x cube times x minus 2. Now obviously px and qx are rational functions, so they are analytic everywhere except those points for which denominator becomes 0. Denominator of px is x minus 2, so px is not analytic at those values of x for which x minus 2 is 0. So x minus 2 is 0 if x equal to 2. Similarly, denominator of qx is x cube into x minus 2. So if we consider this is equal to 0 if x equal to 0 or x minus 2 equal to 0, that is x equal to 0 and x equal to 2. Because denominator of px is x minus 2, px is not analytic at x equal to 2, and qx is not analytic at x equal to 0 and at x equal to 2. Or we can say that px and qx are both not analytic at x equal to 0 as well as at x equal to 2. So both functions are analytic everywhere except these 2 points 0 and 2, because px is not analytic at x equal to 2, qx is not analytic at 2 points 0 and 2. So if we consider any point which is different from 0 as well as 2, then that point will be ordinary point, and this 0 and 2 will be singular points. Px and qx are analytic at every point except x equal to 0 and x equal to 2. So that we can mention here clearly, px and qx are analytic at every point x except x equal to 0 and x equal to 2. Therefore every point except x equal to 0 and x equal to 2 is an ordinary point of given equation 1, and x equal to 0 and x equal to 2 are singular points, because px and qx are both not analytic at these 2 points, and x equal to 0 and x equal to 2 are singular points of given equation, number 1. Now we have to classify whether these 2 points are regular singular or irregular singular. So first we check for x equal to 0, and after that we will discuss same thing for x equal to 2. So for x equal to 0, we have to determine whether these two quantities are analytic at x equal to 0 or not. X minus 0 times px and x minus 0 square times qx. Px is 1 over x minus 2, so we have x times 1 over x minus 2. Value of px is 1 divided by x minus 2. So x into or x divided by x minus 2, and this is rational function. This is not analytic if x equal to 2, at x equal to 2 only. So we can say that this is analytic at x equal to 0, because here denominator is x minus 2, so it is 0 if and only if x equal to 2. So therefore x minus 0 into px is analytic at x equal to 0. Then we check for x minus 0 square into qx, that is x square times what is qx. Qx is 6 divided by x cube times x minus 2. 6 divided by x cube times x minus 2, and we can see this x square will cancel out here, but we will have 1x in the product. This is 6 divided by x into x minus 2. Now this denominator becomes 0 if x equal to 0 as well as x equal to 2. So this function x minus 0 square into qx, it is a rational function, and this denominator is 0 if x equal to 0. So this is not analytic at x equal to 0, which is not analytic at x equal to 0. Therefore x equal to 0 is an irregular singular point. X equal to 0 is an irregular singular point of given differential equation, which we have given number 1 as. So in this way we have discussed for x equal to 0. X equal to 0 was singular point. Then we check whether these two quantities are analytic or not. So x minus 0 times px is analytic at x equal to 0, but this is not analytic at x equal to 0, and therefore x equal to 0 is not regular singular point, or x equal to 0 is irregular singular point. Now we check for x equal to 2. So same thing, we have to decide for x equal to 2. We have to decide whether x minus 2 into px and x minus 2 square into qx are analytic at x equal to 2 or not. Value of px is 1 over x minus 2. So we have 1 here, and 1 is constant function. It is analytic at every point. Therefore it is analytic at x equal to 2. And now we find what is square of x minus 2 times qx. This is x minus 2 square. Value of qx is 1 divided by 6 divided by x cube times x minus 2. 6 divided by x cube times x minus 2. So here this x minus 2 will cancel out, and we are left with 6 times x minus 2 divided by x cube. Now this is also rational function, so it is not analytic if x cube equal to 0, that is if x equal to 0, and in other words it is analytic at x equal to 2, because at x equal to 2 denominator is 8 and it is non-zero, so which is analytic at x equal to 2. This is rational function division of two polynomials. It is not analytic at those points for which denominator is 0. Denominator is 0 if x equal to 0 only. That means this function is analytic at x equal to 2. So we can see x minus 2 times px x minus 2 square times qx, both are analytic at x equal to 2. Therefore x equal to 2 is a regular singular point of given differential equation 1. X equal to 2 is a regular singular point of given equation 1. So in this way we can easily decide or classify the singular points of the given differential equation. And here we find that we are asked to classify the singular points. So first we decide what are the singular points. Here singular points are x equal to 0 and x equal to 2, and we find that x equal to 0 is an irregular singular point and x equal to 2 is a regular singular point. To decide the singular points, first we have to decide the points at which either px or qx is not analytic. So here px is not analytic at x equal to 2, therefore x equal to 2 is singular point. Similarly qx is not analytic at x equal to 0 as well as x equal to 2, therefore x equal to 0 and 2 are singular points. And after that we have to check these two quantities for x equal to 0 as well as for x equal to 2, and we can easily classify the singular points of given differential equation. So they generally ask this type of question for 4 marks about ordinary and singular points. You just have to remember the definitions and you can easily determine the singular or ordinary points of given differential equation. In next lecture we will see how to find out series solution of differential equation. So I stop here. Thanks for watching.